So the differences between moist and dry convection are many. I'll talk about a few of them. As I've just said, there's significant heating of the atmosphere because of the phase change of water. The phase changes can work in both directions. Water condenses as air moves upward, and we'll see why that's so in a minute. But raindrops falling out of a cloud into subsaturated air can and do partially evaporate, and that cools the air. That's important as well. A very important aspect of all convection is the redistribution of water vapor. Water vapor is not a fixed profile, but is in fact determined interactively with the convection. So radiative-convective equilibrium in reality is a two-way street. The radiation drives the convection, and the convection determines the distribution of the most important greenhouse gas in the atmosphere. Indirectly, it also strongly affects the distribution of clouds, which we've seen before are also quite important for radiative transfer. So convection is also a significant contributor to stratiform cloudiness. So here is a very qualitative phase equilibrium diagram for water, showing what temperatures and pressures, what phases exist in terms of temperature and pressure. So on this axis, we have temperature increasing to the right. On this axis, we have water vapor pressure increasing upward. And let's talk about this curve first. This is the equilibrium curve between a planar surface of pure liquid water and water vapor. So along this curve, the two phases are in thermodynamic equilibrium. That equilibrium is given by the Clausius-Clapeyron equation. And as you increase the temperature, the vapor pressure at saturation goes up until you reach a critical point beyond which it's not possible to distinguish these two phases of the fluid. Now, for the atmosphere and water, I should say, for water, the critical point temperature is well over 600 degrees Kelvin. So it's somewhat irrelevant for our atmosphere. This curve represents the phase equilibrium between water vapor and a planar ice surface. So along this curve, ice and vapor are in equilibrium. And along this curve, liquid water and ice are in equilibrium. At this particular point called the triple point, all three phases are in equilibrium. That occurs at a temperature of 0 degrees centigrade. And as you increase the pressure on the system above the saturation vapor pressure at the triple point, that freezing temperature actually decreases. You can melt ice by applying pressure to it, and that's a fairly unusual property of materials. Finally, I've continued the phase equilibrium between water vapor and liquid water down below the freezing temperature here for the interesting reason that in the atmosphere, it's common to see supercooled water, that is liquid water that exists at temperatures below freezing. So that's also an important equilibrium curve for the atmosphere. So how do you form a cloud? Let's go back to this. How do you go from a state where you have water vapor to a state where you have condensed water, either liquid or ice? Now, supposing we take a sample of gas and we bring it to saturation, which we can do, for example, by cooling it. What actually happens when the saturation occurs? Well, it turns out that in the real world, there are plentiful solid or liquid, pre-existing solid or liquid particles called aerosols on which that water vapor can condense. And the condensation of water vapor onto these pre-existing aerosols is called heterogeneous nucleation. If we didn't have those aerosols, it would actually be very difficult to condense water. You'd have to bring the air to quite large supersaturations and low temperatures below minus 40 degrees C to get what's called homogeneous nucleation. Fortunately, in our atmosphere, the aerosols are so plentiful that almost always we can assume that the actual nucleation is heterogeneous. And therefore, supersaturations are observed in general to be very small in the atmosphere, except maybe very, very high up where it's very cold. So for the purposes of this course, and most purposes, in fact, one can assume that when the air reaches nominal saturation, water will, in fact, condense. Now, when it condenses onto these pre-existing aerosol particles. And the initial distribution of water drops sizes are sensitive to the size distribution of these aerosols. And we'll see why that's important in a minute. The time scale for condensation to occur is extremely small, and that's illustrated by this photograph of a cloud that's formed in the shock wave of a jet flying at supersonic velocities. So if you pretend that you're in the reference frame of this jet fighter, air is flowing by very rapidly from right to left. The airplane itself creates a pressure wave. The air goes through the pressure wave, and when it goes through the part of the wave where the air expands toward lower pressure, it cools adiabatically. And that brings it to saturation. And when the air saturates, this cloud forms. Again, the cloud is just very small water droplets. And then as the air recompresses behind the pressure minimum, the water re-evaporates. And the point of my showing you this picture is you don't have to have a lot of imagination to see that the time it takes air to flow through this wave is extremely short, very, very tiny fractions of a second. So as soon as the air becomes saturated, water condenses. The time scale for that to occur is not important for almost everything that happens in the atmosphere. We can assume that condensation is instantaneous. Now, it turns out that when water condenses into a cloud, you can keep cooling the air, you can keep lifting it, and more water will condense. But for typical initial concentrations of aerosols, none of the drops ever gets to be big enough to fall at an appreciable velocity. By that I mean that the fall speeds are usually small compared to air motions in the cloud. And it would take the drops, even if there were no air motion, hundreds of years to actually reach the ground. So condensation is not enough to make drops big enough to fall. And so we have a non-trivial problem. How do you make drops big enough to fall, that are big enough to fall at an appreciable speed? And so we call that the problem of precipitation formation. There are several different mechanisms at work here. There is a process called stochastic coalescence, which is a fancy way of saying that droplets can collide with each other and merge. This is not simple. Often when two drops collide with each other, the surface tension of water causes them simply to bounce off each other or maybe merge temporarily and then break up. And how efficient this process actually is in the real world in merging small droplets into big ones turns out to be sensitive to the initial drop size distribution, which, as we talked about before, is in turn sensitive to the initial distribution of aerosol sizes. So that's one way to form rain. Another is something called the Bergeron-Van Dyson process, and it makes use of the fact, I'll reinsert this slide, that the saturation vapor pressure over ice is smaller than the saturation vapor pressure over water at the same temperature. So if you have a supercool water droplet cloud with very small droplets, and an ice crystal falls into that cloud, the ice crystal, the vapor, will be very much supersaturated with respect to the ice. And therefore, will be rapid deposition of the vapor onto the ice crystal at the expense of the supercool water droplets. So there's rapid evaporation of the supercool water and rapid condensation onto the ice crystals. And the ice crystals can get very big very quickly that way, big enough to fall at an appreciable velocity. Back before the 1950s, there was a brief period in the history of meteorology where it was believed that this was the only way you could get a cloud to rain. All right. But it is important in the atmosphere. Both of these processes turn out to be quite sensitive to how much water you have per unit volume in the cloud water concentration. So shallow clouds, the shallow cumulus that I showed you in the photograph taken from the airplane window, have such low densities of cloud water that essentially they'll never rain. Okay, you never see rain falling from those little clouds. But deep cumulonimbus clouds have enough water in them, have enough concentration of water in them, that these processes can eventually produce rain. But it takes a while. For a tall cumulus cloud, it may take on the order of half an hour or so between when the cloud itself forms and when precipitation might form within it. So the precipitation formation timescale is not small compared to other things going on in the atmosphere.